Hi, my name is Stephanie, and I'm a graduate student at the University of Central Florida, and we will be discussing our project on desalination using a two-dimensional molybdenum disulfide nano-solar evaporator. The picture on the left is our team, which consists of environmental engineers under Dr. Lee and physics and chemistry majors under Dr. Jung. The motivation of our research is that water scarcity is an emerging issue due to an exponentially growing population and the overutilization of freshwater resources. Groundwater aquifers all over the world are the single largest use of water supply. Current methods of desalination are energy intensive and produce discharge that is potentially threatening to the surrounding marine ecosystem. Molybdenum disulfide, or MoS2, is proposed, suggesting a biomimicry to the Namibian fog-basking beetle, which has evolved to gather water from mist via nanoscale bumps on its back. The objective of our project is to improve the efficiency of solar light thermal evaporation and desalination through the development of a two-dimensional MoS2 PU sponge for smart irrigation towards sustainable American coastal cities.
So here we have the fabrication of our MoS2 sponges. To start with, we have our 3D printed scaffold and frame, and this gives us the shape and structure of our sponges and how we want them. And so we take our MoS2 PU solution, pour it inside the scaffold and frame, and after allowing the solution to dry or cast for about 48 hours, we're then able to strip away the PVA layer as it is water soluble. So solely using water, we're able to just attain our MoS2 sponge. Here we can see the solar to heat conversion property of MoS2. As pictured here, we have our solar simulator and our MoS2 sponge directly underneath. Our solar simulator actually emulates actual sunlight, so after leaving our sponge under the light, we observe the sponge to reach a temperature around 70 degrees Celsius after about 10 minutes. We saw this with multiple samples, as after 10 minutes they reached the max temperature of around 60 to 70 degrees Celsius. On our sample without MoS2, no temperature rise was observed at all. So we wanted to test the effectiveness and application of the solar to heat conversion property, in which we wanted to see our MoS2 sponge, how well they can evaporate water. As pictured, we have our two samples, one with MoS2, one without. We submerge them with water and then place them under direct sunlight. Our MoS2 sample reached the temperature around 70 degrees Celsius after around 15 minutes, and our sample without MoS2 only reached up to about 40 degrees Celsius. So then after this, we observed the water mass change in our samples, in which MoS2, after about 40 minutes of heating, was able to evaporate 100 milligrams of water, in which our sample without MoS2 at all actually exhibited no water mass change after being heated for about an hour.
A test was also done to determine the effectiveness of a sponge in greenhouse with salt water. The minimum measured light intensity from the sun was approximately 1271 watts per meter squared, and the sponge reached a maximum temperature of 64 degrees Celsius. Figure B shows that the addition of the MoS2 sponge did result in a larger evaporation rate. The anticipated development of our project is an optimized solar evaporator that will be integrated into a model greenhouse similar to the figure shown, where desalination performance can be tested using seawater and/or wastewater. In conclusion, the MoS2 PU mixture was used for a simple and easy fabrication method. When illuminated, the sponge effectively converted solar energy into heat. The MoS2 PU sponge shows a higher evaporation rate than the regular PU sponge or the water itself. The MoS2 PU sponge effectively evaporated 100 milligrams of GI water in 40 minutes, reaching a temperature around 73.4 degrees Celsius under simulated sunlight. The sponge evaporated 100 milligrams of salt water in 5 minutes, reaching a maximum temperature around 64 degrees Celsius under natural sunlight in the greenhouse. Our project satisfies the three P's: prosperity, people, and planet. For prosperity, the low cost of MoS2 will create economic security. For people, it will provide resource security and positively impact human health. For planet, it will provide environmental sensitivity and resource integrity by only using renewable resources.